Welcome to our self-study online training. This is Lean Six Sigma Yellow Belt training. In this training, we start with the background first, and goal and organization, statistical approach, process capability analysis, and finally, graphic tools. From the beginning, the background, concept and history, what is Six Sigma and Lean Six Sigma, general definition, statistical concept, target, goal, success factors, application. When our science is not developed well, that was the time we think that is a magic. Even quality vision was existing even before, like ISO, zero defect. It's developed to the art. And it's time there are a lot of methodologies occur and develop and still lacking some. Finally, it's developed a lot of high-level methodologies together with statistics and DOE, etc. So that is science level. And Six Sigma methodology allow us to bring the science from magic and art. Let's see. The typical roadmap of Six Sigma is DMAIC. Of course, there are some more roadmap in Six Sigma, DMADOP, DIDOP. But DMAIC is a basic, like a QMS, ISO 9001 in ISO, that is a basic, it's the same. DMAIC is a typical roadmap of Six Sigma. So let's see what is DMAIC. Some people, they call it DMAC.
It seems like I am late again. The bus should have been here by now. I think I have again missed my bus. Every day, I am late to reach the bus stop and I miss the bus. If this continues, I will surely lose my job. God, please help me, so that I reach the office on time. I can see a bus coming, but then I will surely be late for the office. Good that my seniors did not notice that I am late again, otherwise I would have been in problem. But why does this happen with me every day? I need to think about it. Every morning, I am searching for items that I have to bring to the office, and because of this, I get late. But then, what should I do? I think I got an idea. Today evening, I will organize all the things at home and I am sure I will succeed. Now today, I will ensure that I keep the things at the right place so that I can find it in the morning. Yes, my systems work today and now I will get the bus and will surely reach the office in time. I am here at the bus stop in time.
So, let us relook this example of reaching late to office from the DMAIC perspective. In the DMAIC methodology, we first need to define the problem. So, in this case, the define is, I often miss my office bus. Measure is, I am late to the bus stop by 4 to 5 minutes. Analyze is, in the morning, I search for documents that I have to take to the office. Improve is, I have cleared up my shelf of the unnecessary documents. Control is, I regularly clear up my shelf of all unnecessary documents and prepare the office bag in night.
Yes, this is the just simple concept, but don't worry, we'll study more and more deeply. This is just beginning, background. Let's compare the present quality control without Six Sigma, and this is Six Sigma quality control. So what is the difference? Measurement indicator, normally we use percentage, just NG rate. In Six Sigma, we use sigma level, sigma. And data is mostly attribute, discrete, the meaning can countable data. In Six Sigma, we use also attribute together with variable data. Variable data means measurable data. So at first, let's see what is attribute and what is variable data.
The quality of a part can be measured in one of two ways. One way to measure quality is called an attribute measurement. An attribute can be thought of as the presence or absence of a particular quality characteristic. It is generally visual. For example, does a particular part's length fall between 1.4 and 1.6 inches? The measurement would tell you either yes, that attribute exists, or no, the attribute does not exist. The other way to measure quality is called a variable measurement. A variable tells you the degree to which a part meets the requirements. Using the previous example of a part's length, a variable measurement would tell you that this part was exactly 1.52 inches long. Because variable measurements are more exact, we don't need to sample very many parts to get reliable information about a total group of parts. For instance, we might only need to measure the exact length of 5 parts out of 100 to have enough information to believe whether or not the remaining parts are acceptable. If we only used an attribute measurement that told us that the parts were longer than 1.4 inches but shorter than 1.6 inches, we would need to take many more samples to get that same level of information.
We can define attribute data as discrete, means the data is from counting. Number of attendees, number of employees, like that. This variable data, we can call it also continuous data, is coming from measurement, like a weight, temperature, moisture, like that. Actually, variable data give us more information than attribute data. So this is really meaningful. And goal is manufacturing process satisfaction. This one is totally customer satisfaction, more wider meaning. And before we focus on spec out, that means NG, improving. We focus on the failure. But here, even that is spec in, we want to focus on variation improving and together with targeting. And tools for improvement, statistical skills also added. And before is bottom up. Bottom up means from the staff to the top management. Top down means from the top management to the staff. This one normally applicable to manufacturing only, but this one also marketing and service, etc. Let's think about lean. What is lean? There are times US work production, large quantities, rapid pace, high training. And then after World War II, especially in Japan, TPS, Toyota Production System, they have sensation. And then a part of it, just in time. And 1990s, developed as lean. And Six Sigma combined with the lean. So we call Lean Six Sigma. So before that, we have to know the origin of lean is coming from TPS. So we have to know about the TPS, Toyota Production System. Let's take a look at this.
Products is considered by many to be one of the world's greatest manufacturers. This worldwide reputation is based on a specific way of manufacturing called TPS, the Toyota Production System, created to benefit Toyota's customers, employees, and products. So, what does this mean for our customers and their businesses? TPS is an expression of the Toyota Way, a philosophy containing 5 core values: Genshi Genbutsu, Kaizen, challenge, teamwork, and respect. These values are practiced and shared by all Toyota team members at every level in their daily work and relations with others. The origin of this philosophy was first conceived by Sakishi Toyoda, who invented the first automatic weaving loom. Improved versions of these looms would stop themselves automatically if a thread broke, so that product quality could be maintained and waste avoided. However, the true architect of TPS is Taishi Ono, who in the early 1950s drew inspiration from American supermarkets. He marveled at the way the shelves were hardly ever empty because they were restocked so quickly. Customers could choose the exact products they wanted in the exact quantities they wanted. Today, this is called supply-on-demand manufacturing, also known as lean production. This means that the production process will only be launched after the customer has placed an order. Once the production commences, parts arrive just in time at the factory and on the production lines, and the supplies are regulated in accordance with the exact production requirements. Like a pillar, just-in-time plays a key role supporting the Toyota production system. On the production lines, Kanban cards are employed to replenish parts just in time when stocks become low. The time it takes to produce a component or a truck is recorded, and these are called takt times. These times and work cycles are carefully monitored, then coordinated through detailed scheduling called Heijunka. Heijunka ensures that production lines run smoothly, without interruption, even when different products are being manufactured simultaneously on the same production line. TPS is all about creating efficiency. Even wasteful processes and time lost are named. They are called muda. One of the main objectives of TPS is to reduce and eliminate all muda so that time and production are managed with maximum efficiency in a way that does not overburden either an individual, a workforce, or a machine. In consequence, all workers can concentrate on their tasks and deliver better quality products. The second pillar that supports the Toyota production system is Jidoka, or making abnormalities visible. Every team member is empowered to stop the production process whenever a potential fault is detected, so a solution can be found immediately. This means that any problem is made visible on the factory floor and is displayed on the Andon boards as soon as it is detected during the manufacturing process. Should a problem occur, Toyota team members are always encouraged to examine its origins and to practice Genchi Genbutsu, which means going to the source, finding the root of the problem and solving it to ensure production quality. Standardization of the manufacturing process is intrinsic to the Toyota production system's success. Developing and relying on standardized work tasks streamlines the production process and ensures consistently high levels of quality. Overall, Jidoka enables Toyota to provide customers with reliable, durable, high-quality products that offer customers better productivity for their businesses and, in consequence, provide a greater return on their investment. One of the foundations of the Toyota production system is Kaizen. This means continuous improvement. Fundamental to the Toyota production process, Kaizen can be considered as both a process as well as a philosophy. At regular scheduled meetings, team members are invited to give their opinions and share their suggestions for any improvements. Inevitably, these meetings encourage and create teamwork. In a typical year in our European factories, more than 3,000 proposals for improvements are suggested and considered. Perhaps this is why the Toyota production system has also been named the Thinking People system, as it relies on total commitment from everyone involved. TPS is present in every aspect of work and builds respect. All team members are requested to play an active role in keeping work environments clean by employing the 5 S's: sifting, sorting, sweeping, spick and span, and sustain. Clean and tidy work environments benefit the entire production process. Regarding the global environment, TPS is more than willing to adhere to government standards. As the environment concerns both Toyota and our customers, our 3 European factories are all ISO 14001 certified and are fitted with the latest technologies to manufacture products that have the minimum impact upon the environment. Within the Toyota production system, safety is also of paramount importance. Most of Toyota's manufacturing sites are certified or striving for OSAS 18001 certification, so that all team members work within respected standards in a safe and healthy environment. TPS creates a safe and responsible system, producing innovative, safer products that benefit the customers and their drivers. Safer products lead to improved productivity, which creates lower overall costs for the customer. TPS, a unique production system that enables Toyota to face all challenges and manufacture products of the highest quality, products that are cost efficient and whose delivery will be on time. TPS respects the environment and adheres to the highest safety standards. TPS, the Toyota production system, a proven world-class system benefiting Toyota's products, our customers, and our team members. Toyota Material Handling. Stronger together.
Okay. We learn about TPS simply. We can learn more and more later. And let's see. Just in time by Toyota.
I'm Alex Berman, and you're watching Selling Breakdowns. Whenever you buy a complex piece of equipment such as a TV or a car, do you ever wonder how exactly it all came together? Well, ever since the Industrial Revolution, that how has been a vital question for many businesses. Today we're going to look at how in post-war Japan, Toyota helped to create one of the smartest production systems that we have, named Just-in-Time. We'll look at how it works and how you can apply the philosophy and practices to many other areas of your business. After World War II, Japan faced some difficult problems. They didn't have a lot of cash, resources were scarce, and there wasn't a lot of free land to expand factories. However, Taiichi Ohno at Toyota managed to turn these problems into advantages by slowly creating the just-in-time system. The idea didn't come all at once, it's more that through the 50s and 60s, various changes were implemented and improved until the 70s, where the wider world began to realize the benefits and adopted a similar approach. So, what is just-in-time? The philosophy is to make the entire production system only work with what it needs and to minimize wait times between each stage. The biggest savings is normally around inventory. Before just-in-time, a company would keep a warehouse filled with the parts and raw materials it needed. When supplies were getting low, they'd reorder when they had just enough to keep going until the new delivery came. But Toyota realized, what if you just keep making that same order as soon as the next one arrives? That way, you never need to keep this stockpile of spare parts. The cost savings were huge since warehousing is seriously expensive. You need to pay for massive space, power, staff, security, and for all the parts that are just sitting there waiting, not making you money or adding value to your product. And this is the core of just-in-time. You look at each area of production and ask, is this adding value to the product? If it isn't, maybe there's a better way to do it. You cut everything down to its most efficient form with almost no room for error, which is where the risk in just-in-time lies. Toyota used Japan's relatively small size to its advantage. You could rely on suppliers delivering exactly on time because they only had to travel small distances. This is important because if you get problems with supply, it can shut down the whole system. But it's normally worth the risk because the savings are huge on inventory and staff costs. More than this though, you're forced to create a working philosophy that there's no room for error. You don't have spare parts or spare time, so you have to make sure everything functions perfectly. Often, efficiency comes at the cost of quality, but not in this case. In just-in-time, you're forced into quality in order to be efficient. That's why it's applicable to many other areas of business. The best way to think about it is if we simplify everything to two approaches: just-in-time and just-in-case. With just-in-case, you're trying to minimize risk by always giving yourself a buffer. You'll carry extra stock so you can swap out faulty items. You'll overstaff certain areas because they've occasionally had too much work to deal with. You'll support a service that just a few customers ask for. With just-in-time, you don't simply cut these areas and cross your fingers that nothing bad happens. No, you work out how you can avoid them happening in the first place. Because this is money that's wasted unless a bad thing happens, you're effectively investing in mistakes. Better quality control means staff can trust the stock that they have so they don't need a backup. As for workloads, the only reason one department is hit by a workload that they can't handle is because there's not enough visibility between departments. If your sales team know the capacity of production and its current status, then they won't put in an order that can't be filled. And as for offering a service with limited customer appeal, well, maybe you cut it out completely, or you just find a way to merge it with other services so the resources it requires are absolutely minimal. When done well, the just-in-time philosophy should be good for morale too, because the whole point of it is telling your staff, I'm trusting you to perform consistently. And I think most of us respond well to that kind of respect. Want to learn more about business theory and history? Be sure to like and subscribe to be notified of our next segment.
And now, let's take a look about lean manufacturing. Because TPS in USA, they adopted named lean manufacturing. So TPS was transformed to lean manufacturing in Western.
Hi there, I'm Ron Pereira of Gemba Academy, and I'd like to ask you a question. If someone asked you to explain, and I mean really explain, what this thing called lean manufacturing was all about, well, what would you say? Well, by the end of this video, you'll understand and be able to explain exactly what lean is, and you'll have advanced, or perhaps even begun, your personal continuous improvement journey. Okay, well, before we get started, allow me to explain what it is you're about to learn. Well, by the end of this video, you'll know why Lean can and will change the world if applied properly. And you'll also know what Lean is and isn't, as well as its long history. And finally, you'll be introduced to some of the most common Lean principles, systems, philosophies, and tools used today by business, healthcare, and government organizations around the world. Well, let's begin by discussing why any of us should bother understanding or implementing Lean. And to get us started, let's begin with a quote from Dr. Deming, who once said, "It's not necessary to change. Survival is not mandatory." And while it wouldn't be entirely accurate to say that Lean and other continuous improvement methodologies, such as Six Sigma, will solve all of the world's problems, the recent global economic crisis we find ourselves in has made it crystal clear that organizations must be willing to change and improve if they hope to prosper and in some cases survive. Well, in addition to basic survival, let's spend a few minutes discussing some other reasons changing the way we think and operate has never been more important than it is today. First, world markets are definitely expanding, and the need to compete on a global basis has never been more important. It doesn't matter where in the world you live or work, I promise you someone is working to do it for less and at better quality. Next, because of the tough economic times we find ourselves in, our customers are demanding better quality, delivery, and lower costs like never before. And finally, the traditional methods of operating our companies simply don't work anymore. The days of holding massive amounts of inventory and taking months to deliver a product a consumer wants in days are long gone. Okay, well, now that we have a better understanding of the need for change, let's learn what Lean is and how it can help each and every one of us. First of all, Lean is an operational excellence strategy that enables you to change for the better. In fact, the Japanese word Kaizen, which is often used by Lean practitioners to describe the incremental improvements made throughout the Lean journey, means to change for the better. And while Kaizen can lead to quick improvements, the true spirit of Lean is to work with a slow and steady purpose instead of quickly and recklessly. Along these lines, Taiichi Ohno, one of the chief architects of the Toyota production system, once said, "The slower but consistent tortoise causes less waste and is much more desirable than the speedy hare that races ahead and then stops occasionally to doze." Mr. Ohno goes on to say that the Toyota production system can be realized only when all the workers become tortoises. Another common definition is that Lean is the persistent pursuit and elimination of waste. The Japanese word for waste is mura, which describes any activity that's done but adds no real value to the product or service. Sadly, many companies latch on to the elimination of waste aspect of Lean while completely forgetting about arguably the most important aspect of Lean, namely respect for people. So, while we must always fight to eliminate waste, we must never lose sight of our most important assets of all, our employees. Finally, Lean is not only about attacking waste while increasing the speed at which products are produced. You see, Lean is also very focused on improving the quality of our products as well as the stability of our processes. In fact, many Lean principles such as one-piece flow will never succeed without stable and high-quality processes in place. All right, well, in order to truly understand what Lean's all about, it's important to understand its history. And as we'll soon learn, the terms Lean manufacturing or Lean enterprise are actually relatively new in the grand scheme of things. In fact, most people assume that so-called Lean thinking started in Japan by the founders of Toyota. This is actually false. In fact, in 1574, King Henry III watched the Venice Arsenal produce finished galley ships every hour using continuous flow processes. Well, when we fast forward to the year 1799, we discover Eli Whitney perfecting the concept of interchangeable parts, which was another manufacturing breakthrough. Next, in 1902, a young man by the name of Sakichi Toyota revolutionized the manufacturing world forever with his invention of the Jidoka concept. Simply put, Mr. Toyota discovered a way to make his mother's automatic loom stop running when a piece of thread broke instead of continuing to run while creating excess amounts of wasted product. Little did he know, but the concept of Jidoka, or automation with a human touch, would later become a pillar of the vaunted Toyota production system. A few years later, a man by the name of Henry Ford was busy building an American empire called the Ford Motor Company. And in 1910, Ford moved operations to Highland Park, often referred to as the birthplace of lean manufacturing, due to the continuous flow of parts throughout the massive plant. A year later, in 1911, Seikichi Toyoda traveled to the United States in order to study Ford's revolutionary way of producing the Model T. It was shortly after this visit that Mr. Toyoda first began to conceptualize what we now call the Toyota production system. Then, in 1938, the just-in-time, or JIT concept was born at Toyota. The basic premise behind JIT is that we only make what we need when we need it, while downstream processes take what they need from upstream processes. When coupled together with the other pillar of TPS, Jidoka, or automation with a human touch, we arrive at what's often referred to as a TPS Stonehenge, which places the concept of thoroughly removing waste while respecting people at the top. 1949 was an extremely important year in the history of TPS, as a young engineer named Taiichi Ono was promoted to shop floor manager at Toyota. Mr. Ono would soon become one of the chief architects of the Toyota production system. In fact, Mr. Ono was the first person to develop the elimination of waste concept, as well as the first to use Kanban to control the amount of work in process produced within the plant. And while Mr. Ono is commonly remembered for the invention of many of the lean tools we use today, it could be argued that his greatest gift to us all was the way he challenged Toyota associates to think and solve problems by asking why again and again. Next, as the Toyota production system matured and Toyota began to excel as a corporation, the rest of the world began to take notice. And in 1975, the Toyota production system was translated into English, enabling, for the first time, non-Japanese speaking individuals the opportunity to learn all about this amazing production system. Well, up to this point, the term lean manufacturing wasn't actually used to describe the way Toyota worked. This all changed in 1990 as a group of American researchers led by Dr. James Womack traveled the world in order to study the various manufacturing methods in use. And what they learned during their travels was that Toyota was by far the most efficient automotive company in the world. And it was at this time that one of Dr. Womack's research assistants actually coined the phrase lean manufacturing. Well, as it turns out, the term lean, as well as the results of their research, was shared with the world when the book, The Machine That Changed the World, was released. And this brings us to the present day. And while lean is definitely being used to eliminate waste and increase profits in manufacturing environments around the world, lean is also spread to many other areas. In fact, you'll find lean being utilized in office environments where things such as reducing the time it takes to process customer orders is very common. Another area lean has really taken off is in hospitals, where things like reducing errors and the time it takes to find critical supplies has added tremendous value. The military is also attacking waste and variation with both Lean and Six Sigma. And even parts of the U.S. Postal Service have begun their own lean journey, where they've benefited from the use of tools like value stream mapping and error proofing. All right, well, now that we've covered the history of lean manufacturing, it's time to discuss some of the most common tools lean practitioners employ.
Okay, the more we learn about lean and lean manufacturing and Lean Six Sigma. And the next video is just in 3 minutes, Lean Six Sigma.
LSV Group will now give you a brief introduction to Lean Six Sigma. Lean and Six Sigma was originally two different business philosophies and management tools to optimize processes. Today, most companies like LSV Group combine the two methodologies. Let's look at Lean first. Lean is in general about creating most value for the customers with the lowest possible effort. Lean is perfect to reduce waste and increase the quantity of your production or service supplies. For example, look at this block. When you talk about lean, it's primarily about how many blocks you can get through the production at the lowest cost possible without disappointing your customers. But often lean has been associated with the means to make employees run faster, or worst case scenario, maybe even get fired. But it's not true. Lean creates more time for the employees, so they can focus on activities that create more value to the customers. It's about working more effectively so you can deliver exactly what the customers want, while lean in general is about making processes more simple. Six Sigma is about the quality of what you deliver. Now it's no longer just about how many blocks we can get through the production. It's about the quality, the size, the color, and the function. Six Sigma focuses on quality and variation of your company's deliveries. That is because customers don't measure a company on their average performance, but on the specific experience with every purchase they make. Six Sigma strives to get as close as possible to zero errors. But errors can be hard to avoid. So in order to achieve Six Sigma quality, a process must not produce more than 3.4 defects for every million opportunities. So you have lean, which focuses on reducing waste, and you have Six Sigma, which focuses on quality and reducing variation. This means in practice that lean is optimal for analysis between activities in a process, while Six Sigma is suitable for analysis of the actual work that is being done. So, if you're a customer and have ordered blocks, you have now received the correct size and color, and you have received the right amount at the right time and place for the right price. LSV Group's experience shows that by combining the two business methodologies, you can get the best results with the highest net earnings, more satisfied employees, and most importantly, happier customers. Are you curious to know more about Lean Six Sigma? Don't hesitate to visit us at our website, or you can participate in...
Yes, now we can understand what is TPS, Lean Manufacturing, and Lean Six Sigma. Okay, next is about the Lean again. Please take a look. You can stop, you can pause this video and please take a look. And this is the history, the explanation.
Hello and welcome. In this video, we're going to talk about Lean. Let's discuss the origin of Lean. So it was in the 1950s, post the Second World War, Japanese industry was going through a tough phase, and Toyota was no exception. After 13 years of production in 1950, Toyota had only produced around 2,700 automobiles, and they were nearing bankruptcy. On the other hand, American automobile business was booming, with Ford producing roughly 7,000 automobiles per day. So you can see the difference. While Toyota in 13 years had produced 2,700 automobiles, Ford was producing 7,000 automobiles per day. Such a large difference in their production. So in the same year, senior executives from Toyota visited Ford plant in the United States to understand their best practices. Back in those times, owning a car was a luxury. Prior to Ford, cars were mostly custom made for the very rich, produced by highly skilled engineers and designers, and each car was kind of a prototype. Ford introduced mass production with the help of two major changes. First was that they had standard parts which were interchangeable. So it's not that you only are manufacturing one machine. Since they wanted to produce in bulk, they had to standardize the parts so that the parts can be interchanged. Second was the assembly line production. That is, rather than making the workers go to an underproduction car with parts, it was the car that moved on a conveyor from one unit to another for installation, so that there is no unnecessary movement. These are the two qualities that made Ford stand apart when it came to mass production. But Toyota's problems were different. Mass production required huge investments in terms of equipment, machinery, and technology, which was out of question for Toyota. The demand in domestic markets was more of variety, from trucks to luxury cars to multi-utility vehicles and more. Therefore, investments on mass production pattern would have further multiplied because you need a different assembly line for each product category. There was growing competition, that is, established global players were willing to enter Japan. And even if the investments would have been made possible, sustenance was not guaranteed as the technology was rapidly changing. So if today you make a complete setup of mass production for a particular product, due to change in technology, you might have to completely dismantle it or reorganize it. And Toyota was not in a condition to be able to take up that kind of risk. Now let's understand the difference between different production styles. Talking about a batch production, let's say we have a simple task of posting letters. So the first step here would be to get the paper. Then you will write or type your invitation on the paper. Then you will put that paper into the envelope. You'll put a stamp on the envelope and it is now ready for dispatch. Simple 5 steps. So we have different departments. There is a department that brings paper. There is a department that writes or types. There is a department that folds the paper, puts it in the envelope. There is a department that puts stamp. And there is a department that finally dispatches it through the postal services. Everything was moving in batches, and we'll explain in a while what it means. Let's have a look at one at a time production. So you bring one piece of paper, you pass it to the next person. He starts writing or typing the message. The third person starts putting it in an envelope. The fourth person puts a stamp, and the fifth person makes it ready for dispatch. Let's closely analyze what are the differences between these production approaches, batch versus one at a time. So in a batch production system, the product moves in batches or lots. For example, only once 100 papers are counted is when you start writing the first letter. And only when 100 letters are written is when you start putting them inside the envelope. And so on. Which means only once 100 letters are put inside the envelope is when you start stamping them. And only once all 100 letters are stamped is when you start dispatching them. As against this, a one at a time process involves continuous flow at all times. For example, if the first paper is passed to write the message, once the message is written, it is passed to the next person for putting it in the envelope. But after passing the first paper, the person there would have taken the second paper in hand, and as soon as the person who had finished writing the first letter would have given it for putting it in the envelope, the person here would have got a task to write another letter. So that gap which you had in the earlier case of batch production, wherein one task is completed and only then the other task begins, is no longer applicable in a one at a time process. So you can imagine the first letter to be posted would be ready much sooner in case of a one at a time approach versus a batch production. We took an example of 100 here, it could be more or less. So a one at a time approach always speeds up production compared to a batch production. Another very important point here is that while you are doing a one at a time production, you will be easily able to catch defects, and with your feedback you can bring corrections. So for example, if the person folding the letters is not folding the letter properly, in case of a one at a time approach, you'll figure out in the first or the second attempt itself. Whereas in case of a batch or a bulk approach, you will get to know about the first set of defects only when all the 100 letters are there with you to dispatch. So you will not be able to correct it that fast as you can do in case of one at a time approach. And this is the reason against the batch production and mass production, Toyota chose to go with one at a time production. Also, Toyota's entire production system revolves around creating value for its customers. And what is a value? Well, it has three characteristics. One, it transforms the product or service. It is done right the first time. And the third and the most important one is that the customer is willing to pay for it. For a step or a process to be called value add, it needs to satisfy all three characteristics. If it doesn't satisfy even one of these three characteristics, it could be a potential waste. And we'll just talk about it in a while. If in a production flow, a process step is not adding value and is still necessary due to regulatory or compliance requirements, we still keep it. But everything else apart from the three characteristics mentioned above and this one exception that we discussed just now is termed as waste. So what Toyota identified is that in order to create value for our customers, we must eliminate waste, and this was the mantra that Toyota gave. We gave all this background just to help you understand the definition that we're going to discuss now. So Lean is a systematic approach towards waste elimination, which lets an enterprise focus on creating processes that only support value addition for its clients. Now that we know the definition of value and waste, it's easier to understand this definition, and that's where we had to cover those concepts. So this covers part 1 of our introduction to Lean. In our subsequent video, we are going to talk about the 8 types of waste and what differentiates Toyota's production system compared to the other production systems. Hope you liked this video, and if you did, please don't forget to subscribe and share it with your friends too.
And let's take a look, part 2.
Hello and welcome. This is our second video in the Introduction to Lean series. If you've not seen our first video, I request you to go back and see it once before you start playing this video. In this video, we are going to discuss the 8 wastes of Lean and what differentiates Toyota's production system compared to the other production systems. Let's get started. So let's deep dive a little further into the types of waste. There are 8 types of waste that resist value creation. First one is transportation, which is unnecessary movement of products. So you have a product, you have a big shop floor, but you are moving it unnecessarily from one place to another, which is not satisfying the value creation criteria. Second is inventory. So all the raw material, all the work in process step, which is unfinished product, not dispatched finished goods fall into this category. Third is motion. Poor workplace ergonomics, people or equipment moving more than the requirement. So unnecessary movement of people and equipment. As you must see, transportation and motion are closely connected. The difference is that motion involves people as well as equipment. Transportation might mostly be related to the finished products. Fourth one is wait, which is nothing but the delay. Waiting for the next production step, interruptions of production during the shift change. Fifth one is overproduction, so which is nothing but production ahead of its demand. You are manufacturing products, the products are ready, and you're wasting a lot of time, resources, and space to store those products, as those are not going to get shipped immediately. They were never demanded by the customer. And overproduction is often the root cause of other wastes. Overprocessing. It results from poor product design. So you're trying to work on a feature or fine-tune a product to an extent which is not even demanded by the customer. It's not going to add any value to the customer. Seventh one is defects. Effort involved in inspecting and fixing defects. Just to give you a background, prior to the Second World War era, there was a lot of focus on inspection, and quality was primarily driven through inspection. If something is manufactured, it needs to be audited. And if there are defects, they need to be corrected before we ship it to the customer, which is very good. But why should we have a defect in the first place? That defect causes a lot of rework. Eighth one is underutilization of knowledge. This was added later, but it makes a lot of sense in a lot of scenarios. And what it covers is that a skilled person performing tasks that require much lower skill, or his inputs for process improvement are being ignored while decision making. So the right person, say for example you are a senior person and you have a person below you who doesn't know how to draft an email. Now every time that he writes an email, you're proofreading it and correcting it. That's a waste of your time and talent if you're not into the editing business. Likewise, if you are the skilled labor but your inputs and experience is not taken into account by the management while making decisions, that's again a waste of knowledge or underutilization of knowledge. So this covers the 8 wastes of lean. So far we have discussed the difference between one-at-a-time production versus a batch production, where Toyota chose one-at-a-time production, and Toyota further emphasized on identifying and eliminating waste. But there is a lot more that differentiates Toyota's production system compared to other production systems. Number 1, planning and production. At Toyota, these are not segregated job roles. They allow the doers to contribute their ideas for improvement. Now, back in the US, it was observed that planning and production were seen as 2 separate jobs. So there would be a team of highly educated people who will do the production planning and the product designing. And then there will be these low-skilled labor who will do all the assembly and mechanical job. Whereas Toyota advocated that the people who work more closely on the product are the people who should be giving right inputs. Second point is that the standards at Toyota were always dynamic. Now this is very different from what you hear at most of the places. Most of the places will follow a standard which would be a thick manual and people only have heard about it or have referred to some sections of it. At Toyota, they emphasize that we know we will never achieve perfection, but it is always worth trying. They drove standards through visual management rather than heavy manuals. So if you were visiting a Toyota production floor, you will see a lot of visuals placed. Visuals related to the processes to be followed, visuals related to the areas which have been dedicated for certain tasks in particular. It was not to be referred through a manual, but it was to be seen on the production floor. Third one is stop production so that the production never stops. What it means is that in no way a defective product should ever be shipped to a customer. The moment a frontliner identifies a defect in the product, he should immediately stop the production line and get it rectified. Fourth was pull system. So Toyota strongly emphasized that we should never produce until the customer demands. Whereas in batch production system, it was always about manufacturing as many as you can. So it was a push system where you produce more than what's even demanded and you want to store it so that whenever there is a demand in future, you'll be able to cater to it. Now this often backfires in case of products which witness a lot of change in technology. Today, if you manufacture in bulk and if the technology changes overnight, you'll be sitting with a lot of finished products which will be obsolete for the markets. And the fifth one was systems thinking. This was originally introduced by Sir Edward Deming, and it emphasizes that improving the efficiency of specific units or departments alone does not necessarily maximize the overall efficiency. So while a specific unit might be coming back and telling you a success story of their compliance, the product still is not that unit or department's deliverable alone. An excellent product is an outcome of a complete system and not independent units. That's where a system approach or system thinking plays an important role. This covers our introduction to Lean. Hope you like this video and it helps you. Thank you.
And now, let's see Six Sigma and Lean Six Sigma in different aspect. Now is the time the original Six Sigma or typical Six Sigma, where is coming from.
Six Sigma was developed by Michael Hari at Motorola in the late 80s, but has roots stemming back to William Deming and the principles of zero defects and total quality management. Over several years that follow the initiation of its efforts, Motorola achieved a 200-fold improvement in production quality, from 4 Sigma to about 5.5 Sigma, and saved a reported $2.2 billion in the process. Another early adopter was Allied Signal, as they implemented the methods in the early 90s, so that it became more than just a system to measure production quality. Six Sigma became well known after CEO Jack Welch made it the central focus of his business strategy at General Electric in 1995 to drive growth and cost reduction, and in GE's 1999 annual report they attributed benefits of $2 billion net income to Six Sigma. Six Sigma is a compilation of statistical concepts and other tools and techniques put together in a systematic way to get results. In this course, we will look at some of the basic fundamental concepts aligned to the White Belt course.
Okay, Sigma means a variation, standard deviation of certain process. Actually, Six Sigma, the Sigma is a Greek alphabet for S. We call this Sigma. And Sigma means variation, standard variation, standard deviation. Sigma is a measurement indicator for process capability. And the measured Sigma value appears together with DPU, defect per unit, ppm, parts per million, etc. So this is more close to statistical way. Six Sigma quality, this is formula. USL means upper specific limit, LSL means lower specific limit. We call this one tolerance. Maybe you heard about CP, process capability indicator. CP2, CPK 1.5 and zero defect are similar concept, not equal, similar. And 3.4 defects in 1 million. A product or service means almost zero defect. So 3.4, we call it DPMO, defect opportunity in million opportunity. That is, we regard Six Sigma level. So let's check one by one about standard deviation. What is it? Actually, this is represent Sigma. And this one means variation.
How to calculate standard deviation. How many vegetables do you have in your fridge? Is that a common amount, or are you an outlier? We can use standard deviation to know whether someone's behavior is normal or extraordinary. Standard deviation, often calculated along with the mean of a data set, tells us how spread out the data is. It is used for data that is normally distributed and can be easily calculated using a graphing calculator or spreadsheet software, but it can also be calculated with a few math operations. We're going to use an example involving the number of vegetables 5 of our friends have in their fridges. They have 2, 3, 4, 7, and 9 vegetables. To calculate the standard deviation, the first step is to calculate the mean of the data set, denoted by x with a line over it, also called x bar. In this case, the mean would be 2 plus 3 plus 4 plus 7 plus 9 divided by 5, which equals 5. Our average friend has 5 vegetables in their fridge. The second step is to subtract the mean from each data point to find the differences. It's helpful to use a table like this. 2 minus 5 equals negative 3, 3 minus 5 equals negative 2, 4 minus 5 equals negative 1, 7 minus 5 equals 2, and 9 minus 5 equals 4. The third step is to square each difference. This makes all the differences positive so they don't cancel each other out, and it also magnifies larger differences and minimizes smaller differences. Negative 3 squared equals 9, negative 2 squared equals 4, negative 1 squared equals 1, 2 squared equals 4, and 4 squared equals 16. The fourth step is to calculate the mean of the squared differences. 9 plus 4 plus 1 plus 4 plus 16 divided by 5 equals 6.8. The final step is to take the square root. This counteracts the squaring we did earlier and allows the standard deviation to be expressed in the original units. The square root of 6.8 is about 2.6, and that's the standard deviation. We're done. The mean number of vegetables is 5 with a standard deviation of 2.6 veggies. Knowing that about 2/3 of the data fall within one standard deviation of the mean, assuming the data is normally distributed, we can say that about 2/3 of our friends have between 2.4 and 7.6 vegetables in their fridges. To recap, these are the 5 steps for calculating standard deviation. Calculate the mean, subtract the mean from each data point, square each difference, calculate the mean of the squared differences, and take the square root. Using symbols, the equation for calculating standard deviation looks like this. Lowercase sigma stands for standard deviation of a population. Uppercase sigma tells us to calculate the sum for each instance. X is each data point, X bar is the mean of the data points, and N is the number of data points. Keep in mind that there is a similar formula that divides by n minus 1. That formula is used when you only have data for a sample of the population. Hope this was helpful. See you next time.
Yes, standard deviation, the concept is important. Actually, the reason why we use square root, because if not, the value is so big, huge. And sigma is measurement indicator for process capability. Process capability, we heard a lot. Let's see what it is.
Hello guys, in this video I am going to explain you about what are process capability indexes are and what is their importance. In any process, output metrics quantify the overall performance of the process. By observing this, we can come to know whether all customer needs and requirements were met, whether all the business needs and requirements were met. We'll see few examples on what our output metrics are. Consider a paper manufacturing company. In that, the possible output metrics are thickness, fiber content, strength, weight, color, cost per roll, etc. In a room service, the possible output metrics are delivery, timeliness, accuracy, temperature, etc. So, knowing the current performance level of output measure is very important, by which we can find out gap and take proper improvement actions. For this purpose, process capability indexes are very helpful. Process capability index is a metric used to quantify and evaluate process capability. The two most important indexes are CP and CPK. We will discuss about these two indexes in this video. First, we will see what is CP. CP is the ratio of specification width to the process width. In the figure shown in this slide, you can observe the specification width, which is the distance between upper specification limit and lower specification limit, and the process width is plus or minus 3 standard deviations from process average. To say a process is capable, high CP value is required. Generally, the general value is greater than 1.33. It means process is performing within the specification limits. The drawback of this index is it only compares the specification width and process width, so any change in the process average cannot be captured. We'll see few examples. In the first figure, the process is within the specification limits, so CP is greater than 1. In the second figure, the process width equal to the specification width, so CP equal to 1. In the third figure, process width is more than specification width, so process is not capable and needs controlling measures. Now we'll see what is CPK. It compares the width of the specification and width of the process while also accounting for any change in process average. The formula for CPK is the minimum value of upper specification limit minus mean by 3 times standard deviation, comma, mean minus lower specification limit by 3 times standard deviation. So it is the minimum of these two values. So generally, to say any process is capable, the CPK value should be greater than 1.33. Values less than this indicates the process average is away from the target. We'll see few examples. Observe this figure. In the first one, CPK is negative, as process average is too far from the target. In second and third also, the mean is away from the target. In fourth, CPK is equal to 1, as the process met the specifications. In fifth, CPK is greater than 1, as the process is better than the specification requirements. So from these two indices, we can understand a process and can make a decision on either to reduce mean or to reduce variation or to improve both. Thank you for viewing. Kindly post your valuable suggestions and comments.
Okay, the last one we see DPU.
These are two common Six Sigma measures: defects per unit and defects per million opportunities. DPU, or defects per unit, is simply a ratio of the number of defects to the number of units produced, or the total number of defects found in a sample divided by sample size. To calculate, you simply divide the total number of defects by the number of units. Let's say, for example, that you're processing mortgage applications. This month, your organization processed 75 applications, In these applications, 12 errors or defects were found. We would divide the number of defects, 12, by the number of units, 75. There are 0.16 or 16% defects per unit. We multiply the decimal by 100 to find the percentage. So when we multiply 0.16 by 100, we find that about 16% of the mortgages had an error, but we need to remember that a single mortgage application could have multiple errors. Let's say we're making automobiles, and this month we produced 1,000 new cars. Automobiles are complex machines, and many things can go wrong. We found 9,000 defects in our automobiles. When we divide the number of units produced, 1,000, into the number of defects, 9,000, we find that we have 9 defects per unit. Some units may have more defects and some may have none at all, but the average number is 9. Defects per million opportunities. For this measure, we want to convert our defects or errors to see how many there would be out of 1,000,000 opportunities. First, we should define opportunities. Every possible defect in a product or error in a service represents an opportunity. So from our mortgage application example, let's say there are 30 different fields that need to be properly filled out in the application. We multiply the number of fields or places where an error could occur by the number of mortgages processed. 30 times 75 equals 2,250 opportunities for error in our 75 units. To calculate DPMO, we first divide the defects by the opportunities. Then we multiply this number by 1,000,000. In our example, there were 12 errors, and we just calculated opportunities and found that the 30 fields on 75 applications represented 2,250 opportunities for error. Then we divided 12 by 2,250 and we get 0.00533. Multiplying this number by 1,000,000 gives us our defects per million opportunities of 5,333. If you've already calculated DPU or defects per unit, you can use a little simpler formula. You can divide DPU, defects per unit, by the number of opportunities per unit, and multiply that by 1,000,000. As you can see, you'll get the same result. This measure gives us a different perspective regarding errors and defects. Let's turn to our automobile example again. We found that we had an average of 9 defects per vehicle, or 9,000 defects across 1,000 vehicles. Consider that automobiles are complex machines. There are a lot of opportunities for error or defects. Let's say there are 500 opportunities for a defect in each vehicle. Actually, there are probably many more. If we multiply the number of opportunities per vehicle by the number of vehicles, we find that we have 500,000 opportunities for defects. Remember, to get DPMO, we first divide defects by opportunities. We had 9,000 defects, so we divide 9,000 by 500,000. This equals 0.018. We then multiply this by 1,000,000. Again, we could use the shortcut since we have already calculated DPU, and the result is the same. Remember, defects per unit is simply the number of defects found in a sample divided by the number of units in that sample. To calculate defects per million opportunities, we first have to calculate the number of opportunities. We get this by multiplying the number of opportunities for error in a single unit by the number of units in our sample. This gives us the total number of opportunities. Then we divide the number of defects by total opportunities and multiply by 1 million. Or we can use the shortcut and divide DPU by the number of opportunities for error per unit and multiply that result by 1 million. In either case, the result is our DPMO, or defective parts per million opportunities.
Okay, now this is time for study about Six Sigma. Let's wrap up the first class and see you the second class. Thank you so much.